out of it. Okay, so it could be a resin if it's a polymer, but it could also be a metal if it's a metal matrix composite, or it could be so it's essentially the base substratum into which fibers are placed, and these two are made into a single structure which we call as the composite. So all composites have at least two materials, fiber and matrix, and the matrix sometimes called as resin if only polymer matrix composites are concerned, but a more generic term is matrix, which is what we will use throughout the course, right? So that's the matrix that we are talking about. So why do we need a matrix?
So you want it to optimize other properties.
Uh-huh.
So you want the fibers to do one thing and then the matrix will do some other
Right. Okay. So you're saying that fiber is good, but it has certain properties which are not so good. So you want to compensate for that by bringing in an additional material, right? Makes sense, yeah. So again, goes with our hare and tortoise story, where the hare had certain performance advantages because of its strength, but it had weaknesses as well. And so you're trying to do a SWOT analysis, strength, weakness, opportunities, threats, and try to bring in the advantages of both and get the best out of it, right? So what are those issues that using fibers alone will cause, and therefore I need a matrix? Excellent, yeah. So we said that a rod, good in tension, good in compression. Once I keep decreasing the diameter beyond a certain value, your L becomes much larger compared to the diameter, then it becomes a fiber. Bending strength is very less and compressive strength is very less, right? So essentially, if I try to take a strand of my hair, try to push it, I don't even need any force, it just goes off, right? So essentially, it's a geometric failure, but it's like buckling, but essentially it's happening because of very, very low flexural stiffness in the direction, which is a part of which is the compressive strength that you're talking about, okay? So either if you have a compressive stress, or even if you have bending, because bending, remember, is going to apply in the direction which I'm showing the bending. It's going to make the lower parts in tension and the top parts in compression, right? So if I take just a bunch of fibers and try to bend them, what's happening is, yes, they're very good at tension, this will be good enough, but it cannot take the compression, which is why it immediately gives up and it bends a bunch of fibers, okay? Or a single fiber for that matter, right? So that's one of the important things, what Ivan pointed out. Compressive strength, and a fallout of that is the bending strength. Both are very inferior for fibers alone. Anything else? What are the other issues of using fibers alone because of which we need a matrix?
Too small.
Very good, yeah. So fibers themselves, unless you have some manufacturing process specifically for, let's say, filament winding machines, etc., where you have long toes of fibers, most of the fibers are essentially very small. In fact, we saw even the high performance fibers, as long as they are above, let's say, about a centimeter or so, around an inch or so, then they're good enough to be called as long fiber composites, because anyway they're going to not be used as individual fibers but as toes, and therefore breaks in between will not matter, right? So you're saying that because we have short fibers, by themselves fibers may not be able to do what?
Like scale issues.
Yeah. Right. So when you're making very large structures, you need something to bring those short fibers together in order to construct a larger structure. Very good point. Yeah. Anything else? What are the issues with fibers because of which we need a matrix? So already Ivan has brought out some very important points. Anything else that you can think of?
We talked about like with the concrete, like reinforced concrete, like on their own, they have strength, but they're still like they're flexible and they're not very rigid typically. It's like mixed out with a polymer that gives that like its rigidity and strength in the other dimensions.
Yeah. Okay, good point. Anything else?
If you go with the reinforced concrete example, it might protect against degradation by being corrosion resistant. Fibers aren't. I would say that it can provide heat resistance or electrical resistance.
Yeah, excellent point. So lots of secondary things that we need our structure to do, because It's not just load bearing, it has to sustain certain harsh environments like what he was describing, harsh thermal environment. So then the fiber by itself may not be able to handle it, especially in the kind of form factor that it is, very, very flimsy. So therefore the matrix acts like a housing, a protective layer around to take care of that, right? Yeah, good point, Nafis. Anything else, Anai? Okay.
And this cost again.
Cost.
Because fibers are more
Yeah,
expensive.
true,
Few
true.
times.
Absolutely, absolutely, yeah. Fibers by themselves are much, much more expensive compared to a composite where you have both fibers and matrix costs being relatively speaking lower for most matrices, right? So now it's essentially a marriage that we are looking at between the fiber and the matrix, okay, or a live-in relationship to put it in modern parlance. So when you decide to live in with somebody or marry somebody, it's not just because you're trying to fulfill each other's weaknesses, but you also bring certain strengths to the whole party, right? So it makes it better. So what do you think the matrix brings to the composite over and above what the fiber has, right? So far we have only been saying, yes, it's bachelor life is so horrible, I need to get married, right? So now we want to see what is it that the other party brings into the whole picture in order to make this a much more successful marriage. The composite is a marriage of the fiber and the matrix. So what does the matrix bring into the alliance which makes it so good? Okay. So parts of it were already contained in what some things that you said in terms of let's say for example what Nafis said in terms of the containment that is there in order to make sure that the fiber is not exposed to harsh environments, etc. So that's a property of the matrix, a positive property of the matrix that we are trying to bring in. Okay. Instead of matrices, if you can think of resins. Okay. So you start with a resin which is flowing, but then you cure it, it becomes solid, right? Instead of from a semi-solid, it becomes a solid. So then such a solidified resin, what do you think are the benefits of having a solidified resin in a structure? With or without fiber, just by the matrix, what are its strengths? What do you think it brings, other than what Nafis already mentioned?
Easy shaping.
Very good, yeah, important point. Because you know that the fibers, yes, you can shape it in any way, but once you leave it, it can go back to any other shape, right? So it's doesn't stay in that shape. Whereas if you want a particular shape to be maintained, which is very critical in aerospace industry because you want the airfoil shape of the wing cross section. Similarly for the tails, horizontal or vertical. So all of those you want to maintain in a particular way. Yes, there are transverse ribs to do that, but within the material, if there is something that can be done, well and good. And matrix, once it is solidified, obviously retains that shape. So that's a very, very important property. Anything else you can think of a solidified resin? What are the advantages it brings to a structure? Okay, I think you've given reasonably good inputs, most of the important ones. So let's dive into it. Okay. It's an example of a resin getting mixed, and then we want to answer some of the questions of why we are including the matrix. It will essentially be saying many of the things that you already covered in your answers. One is to overcome all the cons or disadvantages that you have from the fiber alone. Okay, if the fiber alone was there, then obviously it cannot support longitudinal compression, which you already mentioned. And because it cannot support compression, bending involves both compression and tension above and below the neutral axis depending on the direction of the bending moment, and therefore it cannot support bending as well. So no compression is possible, no bending loads are possible, and your airplane is all about it because the lift distribution is going to bend the wings upwards, right? So essentially the top skin is going to be under compression. So if you don't have matrix, that cannot be handled by fiber alone. The second thing is poor transverse properties. Remember, I had a plot in the previous class where I showed you Ex by E11 versus theta. That is, if you change the fiber angle, you start from 0 degrees, it's almost 14 times whatever it is at the 90 degrees for carbon fiber, and for many others also it's of fairly large number. Even if you're talking of, let's say, boron aluminum, where the properties are very similar between the fiber and the matrix, even in that case we have a factor of 2 going from 0 degrees to 90 degrees, right? So in other words, if I have a load parallel to the fiber direction, well and good. But if I have a load perpendicular to the fiber direction, or even all the way from 45 degrees to 90 degrees, the properties are so inferior. Okay, so you can't do much with loads on that direction. Of course, a better way to handle that is to have multiple layers, a laminated structure in which you go for cross plies or plies in all the load dominated directions in different phases of flight, so that you can have a laminate which is well designed to take loads in all directions. But if you have fibers alone, obviously that cannot be done because it has very poor transverse properties. How do you do that in the case of when you want to have just a dry fabric, for example? You knit or weave these fibers in such a way that you have fibers in 0 and 90 degree direction, so that if you pull in this direction, one bunch of fibers resists that, and if you pull in the other direction, the other set of fibers essentially resists that, right? So poor transverse properties can be overcome in multiple ways, fabrics and or appropriate design of laminates. But most importantly, even if you before you get there, you're talking about the matrix, which can improve the transverse properties. The second important thing is to go for the positives of the matrix itself. The first one is to overcome the negatives or the limitations of the fiber. The second is to bring in the matrix own important properties, and one of them is to, as you already said, hold the fibers together as a single structural unit. Otherwise, these are all independent by itself, going all over the place, right? The fibers alone. So you want to hold them together in a particular structure, what you call as a structural unit. Then the matrix is what does that, not in its wet state like what is shown here, but once it is cured and becomes solidified, not a semi-solid. The another important thing, and we will see this little more detail, maybe we may not have time to do that, but the matrix has a very important feature, that it helps to distribute and transfer the stresses. So suppose I didn't have the matrix, I just had a bunch of fibers. Okay, and let's say these are joined and fitted somewhere. These are joined as well, right? And I apply a certain force to this. Now we know there's no matrix, okay? It's just a bunch of fibers. I'm trying to pull them all together, okay? St. Venant's principle holds, so only up to a region over here, the actual application of the force will be important. In the interior, it's like a uniform distribution of force or stress that I can take in the interior, okay? So right now, the way I've drawn this, let's say I have 1, 2, 3, 4, 5, 6 fibers right here, or it could be 6 toes of fibers, whatever, okay? But and there is no matrix, it's a fiber only. So now if I keep pulling, I increase the value of this F. At a particular value of F, this will fail, right? So it cannot take beyond a certain value of F. Now I do the same experiment once again with a fresh set of fibers, the same material. Now what I do is I cut one of them over here, right? I don't take any material out, take a pair of scissors, I just cut that, right? So now what do you think would be the maximum value of F? Will it increase or decrease or remain the same? The first example, where all the fibers were intact. Second example, only one of them is cut, the rest are as they are. I continue to pull, only fibers in both cases. First example, I got a particular value of F at which it fails, let's say F0, at which the failure occurred. Second case, will it be more than F0, less than F0, or same as F0? Less than F0, right? Yeah, because you don't have as many team members here, you have only 5 team members, one of them is not there, so obviously, and all of them are doing a similar kind of a job, so obviously it will be approximately 5/6 of the load at which it will fail. Okay. Now let me repeat the same experiment, not with just fibers alone, but bringing this guy in the matrix, putting it in the wet matrix, then doing an appropriate curing process, let's say in an autoclave, going through a set of pressure and temperature cycles so that it's a well cured composite. Once again, same bunch of 6 fibers in one case. In the other case, with a cut, after that I have done this process of putting it in the matrix and essentially getting this done, right? Or it could be possible during the experiment one of the fibers broke, doesn't matter. In either case, will now F0 reduce or remain the constant or increase? What do you think? Only difference between the previous question and this one is now we have matrix. The previous case we didn't have matrix, we had fiber only.
I think it was still decreased, but not as much.
Right, right. So it will decrease in such a small amount that it will be negligible. Okay. For all practical purposes, you will get the same value of F0. Why does that happen? So now, as we said, leave alone the end conditions where Saint Venant's principle is not valid. Only the interiors is what we are taking. So in the interiors, what happens is all of the fibers, if they have the same cross-sectional diameter, which they do, will take the same load. So if it's F0, then it will take 1, 2, 3, 4, 5, 6. F0 by 6 is the load that each one of them was taking. If there was no matrix, it becomes F0 becomes too much, because F0 by 5 would be beyond the failure limit of each one of those or one of those, and therefore it would have failed. Now what happens when there is a matrix is that this thing comes into picture: distribution and transfer of stresses. Distribution and transfer of stresses is that a team game. Instead of an individual game, you're getting into a team game where the matrix and fiber and all the bunches of fibers are all playing as a team, right? So what happens when there is a cut like this? Remember that if there was no cut and I plotted the stress in them, it will be a constant throughout the length, right? The same stress, which is equal to that F0 divided by number of fibers you have, let's say 6, F0 by 6 divided by the area of cross section of each one of them. So that will be the constant value of the stress over there, which will be in the axial direction. So if I want to introduce a coordinate system x1 along this, what the stress that I'm plotting is a sigma 1, 1, because it's on the one phase in the one direction. Therefore the first index is 1 because that's the phase, and the second direction is the direction of the load, which is also 1. So it's sigma 1, 1. So sigma 1, 1 will be a constant in each one of them, right? Now on the broken fiber, if the matrix were not there, then what happens is all of this just in that fiber alone just comes to 0, right? So it's just 0 over there throughout, which means the other fibers have to take all of that load redistributed, and which is why it failed first. Now what we have is a situation where we have the matrix inside. What happens is that where it is cut, so if I draw this particular portion over here in an enlarged way, so essentially I have the I'm drawing the separation in an exaggerated way, but to start with, it will be just almost in contact, and then slowly, because of the load that is there, there might be a slight separation, but it's of the order of the same order of magnitude as the diameter of the fiber. Now what happens is, because it is broken, the stress here, that sigma 1, 1 that we were talking about, and the stress on this sigma 1, 1 is equal to 0. That's the boundary condition that you have there. Whereas where it is attached, it still has, if I cut there at that particular location, you would still have that same sigma 1, 1 which was over here. Let's say sigma 1, 1 naught. That same sigma 1, 1 naught will be there. So in other words, it has to build up from 0 to that particular large value, and in fact it doesn't take all the distance to do that. It's just of the order of magnitude of this diameter, which is of the order of 10 microns, let us say. So just about 10 microns into it, you will see that it will be 99% of sigma 11 naught is already reached. So same thing with this. So it's only a very, very small portion of the fiber which has become ineffective. Most of the fiber remains. Why that happens is because of the matrix that is surrounding this. So that matrix, immediately as soon as it sees a cut, it transfers that extra load to the next fiber. The adjacent fibers that are there, that get shared. So this fiber that is there and this fiber that is there, they start sharing this load, and therefore very quickly they let the fiber to pick up. But the matrix cannot take very large axial stresses. The way it takes is by shear stresses. So the matrix undergoes what is known as a shear stress, and that shear stress compensates. If you take a free body diagram, you can do that. In fact, your textbook, Bauschow and Craig, has very beautifully described the mathematical derivation of this into some simple ordinary differential equations you can solve for, and using the boundary conditions that I just described, and then you can come to that, and in fact you can prove that it's about 99% it reaches within about a fiber diameter. You can actually show this in a generic sense, not just for any specific fiber or matrix, but pretty much for every fiber and matrix, that as long as the fiber and matrix are doing their jobs appropriately, you will see that. So now you see the importance and relevance of this particular functionality of the matrix that we're talking about to distribute and transfer the stresses, because without that the overall performance of the bunch of fibers will be much more inferior. The stress transfer will not take place between broken fibers. Is this clear? Because this is a very important topic in terms of stress transfers. Okay, though we're not going into it quantitatively, qualitatively understanding this is important. The next thing, I think Nafis already brought this up in terms of temperature, but there could be other aspects of the environment like humidity, etc. Many other aspects from which the fiber is eventually protected, because it is surrounded by the matrix, almost like a bulletproof jacket that it has, and therefore it's doing a lot of good for the fibers in terms of taking care of some of the spikes in environmental conditions like temperature, pressure, etc. Right? Also corrosion. So next is in terms of again, it depends on the kind of matrix. So far we've been talking only about polymer matrix composites, which are mostly used in a lot of aerospace applications, but slowly, especially for higher temperature applications, we have started moving into metal matrix composites like aluminum matrix or titanium matrix, even where silicon carbide fibers are used, for example. So when you have metal matrix, then unlike polymer matrix, which are brittle, the metal matrix, just like any metal or metallic alloy, is ductile. So you can get the best of both worlds. You can get those ductility aspects of the metal as well. But metal brings in higher density, so the weight advantage that we were getting with polymer matrices, of course, is not there. But the temperature capabilities, the ductility, and therefore manufacturability, etc., those things are there. The other thing is in terms of the energy storage, because it's a brittle fracture for polymer matrices, the toughness is very low because it doesn't have a spread in the inelastic regime, and therefore the stress strain curve abruptly stops, and therefore the area under the stress strain curve, which is a measure of the energy per unit volume, is much lesser, which is the toughness is much lesser. But with metal matrix, that can be increased, right? Similarly, in terms of electrical insulation, especially if you want conduction, then metal matrix is good. If you want, let's say, insulation, polymer matrix is good. Even ceramic matrices, which are very good insulators, are good enough. So you can essentially bring in these aspects also depending upon the specific matrix that you choose. Okay, having said all that, pretty much the choice of the matrix depends primarily on the service temperature. One is of course the compatibility with the fiber, because you need to ensure that the fiber and the matrix are not going to be chemically reacting with each other and therefore forming some other compounds which are not having good structural properties like stiffness or strength. So then you have an issue. One most important thing you have to make sure of is the compatibility. But then the overriding factor, once compatibility is ensured, you will still have a huge short list of matrices that are possible to be utilized, and one of the main reasons you choose would be service temperature. Today, of course, it's also becoming important to ensure sustainability, so environmental issues. Therefore, we are moving from thermosets to thermoplastics like polyether ether ketone instead of epoxies, even though there are certain manufacturing issues, but most of them are for aerospace industry are kind of resolved. But traditionally, and even today for a large part, I will ask, once I have decided on the fiber, I have a bunch of matrices that can go with it, then I will ask you what is the typical temperature range you expect for that component in service during its life, during various flight phases of takeoff, landing, climb, descent, cruise, maneuvers, etc. What is the maximum temperature it can reach? What is the minimum temperature it can reach? And based on that, I have to choose a matrix which can sustain that temperature range, and it's usually the maximum temperature which determines that. So most of the classical matrices that have been used with composites, like the epoxy, are essentially thermoset polymers. So in other words, it gets set and you cannot reuse it, you cannot reheat it to reshape it in any particular way. From the name itself you can make out. There are many other subtle differences between thermosets and thermoplastics. We'll not get into that, it's a topic by itself. But again, thermoset polymers are a wide range of wide family. Within epoxy itself, there are many different kinds of epoxy. Polyester is another example of a thermoset resin. So most of these will take you all the way up to 150 degrees centigrade and not more than that. So if your component is going to experience temperatures beyond this, then this is no good. But in most aerospace structural components, especially the primary components of the wing, the fuselage, the tail, etc., they all typically do not go even up to this temperature. So therefore, thermosets were good enough, epoxies were good enough purely from this point of view. So now if you go all the way up to, let's say, 425 degrees centigrade, then you can bring in, as I said, PEEK, polyether ether ketone, or nylon, which are examples of thermoplastic polymers, and therefore you can go. So again, these are, don't take these numbers as sacrosanct. There's a wide range which is possible. There can be a few outliers for thermosets which can go beyond 150, or thermoplastics which can not go all the way up to 425, it can go only much lesser, etc. But just trying to give you the trend in terms of the overall families that are involved. Now you go for engine kind of applications, especially close to the combustion chamber, but in the frontal portion, like the turbine blades, or not the turbine blades, the compressor blades, or the turbofan in the fan itself, etc. Those portions you can probably have even higher temperature than 425 degrees centigrade. Then you have to go for metal matrices like aluminum, or more usually titanium alloys. Then if you have even higher temperatures, especially for a lot of space or re-entry kind of applications, then you have to go for ceramic matrices, examples being borosilicate glass, and that can take all the way up to 1650 degrees centigrade. Okay, so then you have, especially for the frontal portions of the re-entry vehicle, where the aerodynamic heating is phenomenal, there you have to go for a carbon-carbon composite where the matrix is also carbon, and therefore it can go as high as 2760 degrees centigrade. So very important to remember that yes, there are many functionalities of the matrix, but more or less all matrices will do that for you, but the specific choice of matrix has to be based on physical chemical compatibility with the fiber first of all, and once that is done, purely based on the service temperature, because that determines whether the matrix will survive or not, and therefore once the matrix is gone, the fiber can't do much by itself, as we already saw. and therefore it could be a disaster. Therefore, you have to ensure that you have a very proper understanding of the component that you're designing, not only the mechanical loads that it is going to experience, but also the temperatures and other humidity, etc., that it's going to experience, so that we can take care of all of these. As we said, there's a possibility of the polymer swelling, etc., in humidity. So you have to make sure that those are not major issues. Corrosion, especially if it's a marine environment in which it is operating, like on aircraft carriers, the naval aircraft, etc. So you have some special requirements there also. But this is more or less the generic way in which we try to understand various types of matrices depending upon the temperature of the components that the components will be exposed to during its service life, or even during the manufacture for that matter. Okay, so yeah, I think we have time for this. So remember, the questions that we are asking in all situations is what, why, where, and how. Okay, how is what is most important for us engineers, but if we have not understood the W words, that is what, where, and why, then the how doesn't make much sense. It's just mental gymnastics that we are doing with the math over there. So which is why very important for us to spend at least a few minutes with each of these questions before we get to how, which is the dominant portion of the course. So where are composites used? Your previous homework was an answer to that, where you took up Indian aircraft like Saras, Advanced Light Helicopter, the Light Utility Helicopter, LCH, Light Combat Helicopter, the launch vehicles, Polar Satellite and Geostationary Launch Vehicle, etc. For each one of them, you showed the materials that are used, including the composites, and you showed which part of the vehicle is made out of composites and why, right? So we will see a few more examples and then we will get going with how. Okay, so some examples, classic examples, all the way from satellites to don't remember exactly what this, anybody remembers what this could be a part of? Maybe a launch vehicle or something, right? So this is a filament wound structure for a pressure vessel, typically like a rocket casing, rocket motor casing, especially for solid rocket motors, where you will have propellants loaded on the interior and have a particular burn configurations on the interior to start with, and then of course various aircraft and helicopters, right? So it's used quite extensively in all of these vehicles, whether flying in air or in space. In space, partly in air and space, like rockets and missiles, which have a part of their flight path in air and part of their flight path in vacuum. Then those which fly entirely in the atmosphere, helicopters and airplanes, either the Earth's atmosphere or those which are made for various planetary explorations, very rarefied atmospheres like Mars, or very dense atmospheres like Venus or Titan, the satellite of Saturn. So these are all things which are being designed currently or already designed and experimented with. So that's another example where composites become critical, because more the performance requirement, more it is. And automobiles, especially the racing cars, etc., but today even a lot of the regular passenger cars are being made out of natural fiber composites, for example, like jute fiber, etc. So those are becoming quite common, and it's a win-win situation for a lot of industries and agriculture as well, because a lot of these are waste products from agriculture which can be used as fibers. And so in general trend, we are moving towards sustainable composites. Fiber alone is not enough. As we said, matrix also needs to be natural, right? Then static applications on the ground, wind turbine blades, because a lot of interest in renewable energy. Huge wind parks are coming up all around the world. The Scandinavian countries are historically famous for that because of their large wind speeds and also the kind of technologies that they have developed and patented over a long period of time. India is also going really big in terms of solar power and wind power. So wind turbine blades, which are really massive, huge, running into many meters of length, and if you make them out of metals, the weight is going to be phenomenally high and the stresses are going to be very large because of the centrifugal forces, etc., and therefore composites are very extensively used there as well. In fact, a lot of the Scandinavian countries' research offices are situated in India, especially in Bengaluru, and I teach a lot of composites courses for some of them, and their challenges are sometimes of a different kind, but in that different kind it's much more challenging. So that's another very interesting area of research for those of you who are thinking of composites for non-aerospace applications, but still a lot of carryover happens from the helicopter main rotor, how it works, to the wind turbine blades. There are of course subtle differences as well. Then another important application where we worked on while I was at Georgia Tech was on offshore structures and also transfers from offshore structures to the mainland. So typically oil is extracted in a lot of these undersea drills, and then you want to export that oil. It's not always carried by ships. There's a pipeline which goes all the way to the mainland, and these pipelines can run hundreds of kilometers. Okay, some of these were earlier made out of metal like aluminum pipes or steel pipes, etc., but corrosion had become a major issue both from the oil and the outside marine waters that are there, the salty water that is there. So people started moving to composites, but then when you're trying to join two composite pipes, because you can't have hundreds of kilometers a single pipe, right? So you have to bring two pipes every now and then to join them, and these pipes can undergo, because of the changes in temperature of the water, they can undergo expansion and contraction. So which means the joint should be capable of that. So many of these composite joints are actually manufactured out of that, and that's some of the designs that we did while I was at Georgia Tech. Another example of an application of composites non-aerospace is containers. These are on the ships for transporting tonnage of weights from different countries. So those are massive containers. Now if the containers are made out of composite, a huge amount of that weight which is saved going from metal to composite is now can be used as more payload. So you can carry heavier things in those same containers, and therefore it really helps. Piping already mentioned. Sporting goods, we've been talking about it in the morning as well. Some of the cutting edge sporting goods are made out of that. A lot of avionics, especially on the aircraft. I think I probably mentioned this earlier, that avionics costs of the aircraft is much more than most of the other costs on an aircraft when you initially buy an airplane. So that avionics, a lot of it, the printed circuit boards, etc., earlier made out of polymers, now are getting made out of composites, and some of these the fibers are being used actively, not only as a part of the structural load bearing, but also in terms of the circuit itself, to see how that can be blended into a multifunctional kind of a structure. So that's avionics. Then quite a few electrical appliances, high-end electrical appliances use some of these composites, but these are all kind of outliers. The more important thing is the transportation sector, where lightweighting is very critical. Okay, some actual examples from the Indian aerospace industry. Some of you talked about the helicopters made by Hindustan Aeronautics Limited. We were lucky, as I said in an earlier class, to work on one of their design changes, especially for the tail rotor, to get a structural health monitoring system in place, because of which we worked with some of these. So one example of that is what is known as a trapeze effect, where the extension and the twist are coupled with each other. Extension due to the centrifugal force, twist due to the pilot's controls, as we talked about earlier, the cyclic pitch stick and the collective pitch stick, and the aerodynamics that is there, and the 90-degree phase lag that I was talking to you about, increasing the pitch and increasing the flap. So if I increase the pitch over here, the flap actually increases here, and if I decrease the pitch over here, the flap actually decreases here, so that the tip plane of the helicopter rotor blade, instead of being horizontal, now feels like this, and therefore the net thrust is always perpendicular to that. And so there is a component which is balancing the weight. There is also now a component which is trying to take the helicopter backwards, right? So similarly, you tilt it forward to the left or right to make the helicopter move in all those directions. Now, most of this was done by actually manufacturing these blades in a pre-twisted condition. So that's when no load is applied, this will be actually pre-twisted. But now with composites, you can have what is known as the antisymmetric layups. If one layer is plus theta, theta could be any value, I put another layer which is minus theta, right? So now this acts almost like a pre-twisted beam, because if I try to pull this, what happens is this tries to straighten out, like, which also makes it kind of twist, right? So this kind of combination of manufacturing with a certain pre-twist and then having about the mid plane at any given distance, if you have, let's say, 30 degrees, at a equal distance over here you have minus 30 degrees of the same thickness. At some distance here you have a minus 45, here you will have a plus 45 to balance that out. So that above and below the mid plane you are having the same set of angles in magnitude but opposite in direction, which means that you will have a bunch of fibers like this, right? So all of them, when you are trying to pull, of course it will extend, but it will also twist. If you are trying to twist it, of course it will twist, but it will also extend or contract. Okay, so this is a huge advantage for a lot of these applications, whether it's wind turbine blades or helicopter rotor blades, and that's something that we have tried to extensively utilize. And taking this forward to some of the multifunctional composites like piezo fiber composite, the sensing and actuation are also coupled in this way. So if you want to sense something which is a small twist angle, I can do that by sensing the extension, which is much easier to sense, and then I can make a calculation of what the twist is. So these possibilities are what made a real-time structural health monitoring system possible for such aircraft. Here we are talking about, in general, they exhibit extension twist coupling, which is similar to the rotor blades with pre-twist because it's anti-symmetric layup. Symmetric means if at above the mid plane, if there is a theta, below also there should be a same sine theta. Okay, if there's a minus theta here, there should be a minus theta at the same distance here of the same thickness. So that's symmetric layup. Whereas anti-symmetric is, if you have a theta, you should have a minus theta of the same thickness on the opposite side. So that kind of a thing behaves very similar to having a actual physical geometric pre-twist that you do in the manufacturing. Like many of these fans, if you look at this fan, you see that it's not actually straight, it has a small twist there, okay? Like what in the wings that you say as wash out or wash in. So something similar to that, you have a twist there. So it's much more pronounced in the case of helicopters and wind turbine blades. So used in aircraft propellers also. Fixed wing aircraft also have propellers. If they are turboprop, for example, or piston prop, the older kind of aircraft, you will have propellers there. So those have very large twist, as you would have observed. Then you have the short takeoff and vertical takeoff and landing vehicles. Those typically have like tilt rotors, where you can use the same rotor for forward propulsion like an engine or upward propulsion like a helicopter. So two different modes of the same thing. The Osprey was a classic example of that, Bell Osprey. Then helicopter flex beams, which I've already talked about earlier. Okay, so is an example of the Osprey, which is a tilt rotor mechanism. And you would see that if it's for vertical flight or hover, the kind of requirements on the blade is very different from the forward flight, and you can make those differences by changing the twist angle through the pilot controls. And you can bring in some of those couplings a priori by manufacturing with a certain pre-twist and with certain anti-symmetric laminates. Okay, I think yeah, I'll probably take 2 or 3 slides which are mostly about where composites are applied, and we'll finish. Okay, so now this is the advanced light helicopter, which is christened as Dhruv in the Indian parlance, and it's been exported to quite a few countries as well. It's been around for quite a while now. The Dhruv's tail rotor flex beam, this is the kind of geometry it has, much simpler compared to many other aircraft components. Now if you look at it, it's a hybrid kind of a structure. The lighter yellow colored ones that you see are glass fiber epoxy composites. The dark black colored ones that you see are carbon fiber epoxy composites. So this is just a section view of that. You see that over the length you want to drop off the plies, because as I said earlier, helicopters were fully articulated. They had a hinge in this direction, they had one more hinge in this direction. This is called the flapping hinge, lead lag hinge, and then there is a bearing called the torsional bearing or the pitch bearing. Now most of today's helicopters, modern helicopters, have done away with those two hinges and bearing. You have hingeless, bearingless helicopters, which means that the blade itself should have a taper. In other words, it changes its thickness so that there's a thinner portion which kind of acts like a pseudo hinge. A hinge has the capability of taking no moments, okay? It has no resistance to moments if it is well lubricated. But here you will have a small resistance, but compared to this bending stiffness, because the moment of inertia is very large, EI, the bending stiffness is very large, whereas here it is much lower, and therefore it's almost acting like a pseudo hinge. So flex beam ply drops to simulate that flapping hinge is what we saw in the previous slide, the way it is actually applied in the groove. And the reason, of course, you have the carbon fibers on the outer and the glass fibers interior. Anybody can guess why it's not the other way around, that the glass is outside and the carbon is inside? Why is it not like that?
More brittle, more
True.
exposed to like
True. True, but that's a secondary reason. There's a primary reason why this is done. Remember the triple functions we talked about when we were talking about any aerospace structure, and one of them was like all three of them led to the conclusion that you move them outwards, it's better, right? That's why we said I section or thin circular tube are good for bending and torsion respectively. Here it's just a rectangular cross section, right? If I cut through this, it's just a rectangular cross section, okay? So now we're talking of bending in this way, it's just flapping, right? So you want the stronger and stiffer material outside, right? Because the inner is close to the neutral axis, hardly takes any stress, right? So there's hardly any stress at almost the middle over here. So the glass fiber is not that good in its stiffness and strength compared to the carbon fibers. So you are putting carbon fibers on the top and the bottom to take most of the bending stresses, tension as well as compression, whereas the shear is mostly taken by this. This is almost like a sandwich. We talked about sandwich earlier, remember? A core, and then we have the top phase and the bottom phase sheet. When we dealt with one of the three design criteria, we talked about a sandwich plate. And there also we said that the phase sheets take the tension and the compression in bending, whereas the intermediate core, whether it's an aluminum honeycomb core or a foam based core, or for that matter something like this where it's entirely composite, you have all epoxy matrix, but on the top you have carbon fibers, bottom you have carbon fibers, and in between you have the glass fibers which are less stiff, and therefore the glass fibers are mostly taking the shear loads. Because of the lift distribution and drag distribution, there's not only a bending moment in the two directions, bending this way, but also a shear force. So if you draw the shear force diagram, you'll see there are certain locations where the shear force becomes very large, which is closer to the root or the hub where the helicopter rotor blade is attached over there, and there you would see that you have this kind of a geometry will help to take the shear loads through the glass fibers and the extension, compression, bending, flexural loads because of the carbon fibers. Okay, so with this we'll stop for today, and the next class will be on Wednesday, which is online. Thank you. If you have any questions, I'll be happy to answer.
about thermostats and thermoplastics.
Uh-huh.
So you like when you showed the slide with 150 Celsius and thermoplastics.
Yeah.
So do you mean like what temperatures they can withstand in a way, or because like thermostats can like get?
Yeah. So this is. See, each of them have a large family of examples. I've just mentioned one or two in each case. So it's typically a ballpark value once again, just like we were comparing when we are comparing the ultimate strengths and the Young's moduli of various metals, etc. We said a lot of alloys, but we're just comparing a typical value. So this is like a typical value there. So it's essentially qualitative sense this way you go. For lower temperatures you use thermosets, a little higher temperature you use thermoplastics, even higher you go for metal matrix, further higher ceramic, and the highest capable today is carbon matrix. But as I said, there could be some thermosets which can go in this range, and there could be some thermoplastics which go in that range. So that's a possibility, but more or less This is how it is. Yeah. Anything else? Okay, thank you. See you on Wednesday.